Okay, second week, fourth topic. So, Unit 4, we're going to talk about manometers and pressure measurement. Okay, so this is really short and sweet. Okay, what do we have here? Okay, so for this section, you're going to become familiar with pressure measurement devices. So I know we talked about a couple different ones in the last video, but so manometers, pressure gauges, pressure transducers, and transmitters. So there's going to be two handouts. So they are uploaded to week two's folder on D2L as well, but we'll go over them real quick and then you can read them on your own time, okay? What do we have here? So manometry? Okay. When we discuss pressures, we looked at the example of a barometer, which is an example of a pressure measurement device known as a manometer. So manometers use the relationship in pressure and the change in elevation of a static fluid. Again, the fluid cannot be moving. So like for air, it's wind, waves, river currents, that kind of things. Or say if you work in a like a pulp and paper mill, so there'll be lots of fluids that run through all those pipes in there. So manometers use this relationship. So this change in pressure is in the elevation of the static fluid. So the change in pressure is equal to the specific weight of the fluid times the height. There's also this piezometer, it's called. It's a fun little word, isn't it? So it's a type of manometer, and it uses a simple vertical tube, like a standpipe, and it's attached to a source of liquid under pressure. So either a pipe or a groundwater, so any kind of liquid that's under pressure. So the tube is sufficiently long enough that the liquid can run freely within that length of tube, but not like overflow at the top of the tube. Okay. So the height of the liquid in the tube gives a value for, it's called pressure head, and it's in units of length. So it's denoted as H in this course. So pressure head is obtained by rearranging this change in pressure is equal to the specific weight times the height, and is given by the height is equal to the change in pressure over the specific weight of the fluid. Okay. So now I need to say this. So the specific weight, it can be the specific weight is just the specific gravity times the specific weight of water too. So we got density, we've got specific gravities, we got this specific weights, all that stuff, remember from the first week. Just keep that in mind, okay, when we're doing these calcs. So a piezometer tube should be less than 10 millimeters in diameter to avoid excessive capillary action. So remember we said before, I think it was less than or greater than, so this has to be, the tube has to be greater than 10 millimeters so that you're not getting this weird capillary action. The same setup that we learned, remember we learned that in the last video, the same setup can be used to measure the pressure head at a point in a flowing fluid, as long as precautions are taken in the connection of the piezometer to the pipe to avoid effects of velocity and turbulence in the connections from altering the reading. So if you put a piezometer down a pipe, there's, like we talked about how there's water in pipes flowing under the ground in urban areas. Generally, you probably have had to deal with some of this in maybe some of your courses just by looking at pipes. If that fluid is under pressure, and if you put this piezometer in there and make sure, it's all very specific and calibrated and blah, 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 you can figure out the pressure within that pipe. So height of the column. The piezometer introduces this piezometer. Introduces the concept of expressing the pressure as the height of column of a liquid. So this pressure head, H. The expression does not have to be made in the same liquid that is being measured. So for example, when measuring air pressure, so that air is the liquid, the readings are often given in units such as in H2O, so in water, or inches of water column. Mercury is also used, so that barometer that we talked about last video. So if you look at section 3.8 in the book, and appendix 8K provides conversion factors for examples. So 1 inch of mercury, Hg, is equal to 0.491 psi. 1 meter of water is equal to 249.1 kPa, which is equal to 0.0361 psi, pounds per square inch. Okay, so there's a bunch of little conversions in there. We'll be using them. So piezometers use the same liquid as a measured fluid as in the pressure source, and are limited in pressure, and then can be due to the physical limitations of the tubing height. So I mean, you can imagine that they can't make a tube, you know, well they could, but it'd be weird looking, a kilometer high, right? Or whatever, you know, there's some physical limitations to this. So manometers utilize different fluids to take advantage of different specific weights in the equation, so that change in pressure is equal to the specific weight of the fluid times the height. So remember mercury, that's why mercury's in there a lot. For identical pressures, a fluid with a specific weight, the higher density, will be given a smaller rise in the manometer tube. In other words, the change in pressure, which is equal to specific gravity, specific weight times the height. So delta, the change in pressure is constant, and it's that density, that specific weight of the fluid that changes. So pressure head will vary. Okay, that H, remember. So here's something called a U-tube manometer, not to be confused with the YouTube that you're watching this video on. It's the simplest kind. It's open-ended at one side, so usually at 1 atmosphere, and at this point, if it's 0.1, you'll see in the diagram, we got a blue liquid, which happens to be water, and we got a green liquid, which is mercury. So at 0.1 there, on the green liquid, that's open to the atmosphere. And one end is connected to the pressure at point A. So that's what we're interested in. What's the pressure at point A? So what do we do? Okay. So the liquid in the manometer is called the gauge fluid. So the mercury in this case, okay. So the green fluid. So that's the gauge fluid. The gauge fluid and the fluid to be measured must be immiscible, so they cannot be able to mix, right? So if they mix, then this doesn't work so good. So they have to have quite a bit of density difference. There's some other little things that we'll get into later on, okay? The gauge fluid is displaced by the fluid to be measured by just solely by the pressure, okay? So this gauge fluid, mercury in this case, is going to go up and down depending on what the pressure in the water is, because that's what we care about, the pressure at point A, if the pressure is changing. But anyway, so the gauge fluid is at rest, and we can apply, once it's at rest, you know, once it stopped moving around and doing whatever, the change in pressure is equal to the specific, like all of them, right, linearly specific weight times the height. Okay, so that's one type. There's also this other thing called a well type manometer. Fluid level of the well drops a small amount while level in the manometer tube rises a larger amount in proportion to the surface areas of the well and the tube. So this well, you can see where it says measured pressure, original level. It's surface area is a lot bigger than the surface area within the tube. You can imagine you've got like a giant well, or a well enough to support a family, and you're not going to have something so big on the outside to try to measure what the pressure, and you've got a smaller tube. So this is used to read small pressures, and it has to be calibrated so that you can read it directly. So we'll get into it. Some applications here. There's an incline manometer, just as the name suggests. It's an incline scale. So it's the same as the well type, but it's used on an incline scale to give greater sensitivity. So say if you care about smaller drops in pressure. The scale is calibrated so that you don't have to make any guesses, right? It's all just is what it is. And so here the change in height, so that pressure head is divided by the length of the ruler is equal to the sine of the angle. So the angle between on the incline, so sine of theta equals opposite over hypotenuse, and there it is. Similar manometers can be used to read small pressure changes between two pipes or pressure sources, depending on what you're trying to measure, right? It's a differential manometer, and these are used with gases. Each end is attached to a pressure source, and the inclined scale gives a larger scale for smaller changes. Okay. Differential manometer, so this is what I have to deal a little bit more with. So indicates pressure differences between 2 points, point A and B in this case, and it's not the actual pressure at either point, it's just the differential between the 2 points. Differential pressure manometers are typically used for flow measurement devices such as flow nozzles, orifice plates, or a Venturi meter. You'll hear these words throughout the course, Venturi meters and all that stuff. These are known as variable head flow measures. So you can see this little diagram here. We've got a flow in a pipe. It's flowing from left to right. We've got a couple of different areas, a bigger area and a smaller area. So, and then the change in height in the fluid is going to be that pressure head. As you can imagine, if a flow goes from a bigger area into a smaller area, there's going to be some changes. We will get into those calculations throughout this courses, so the pressure is going to change. So they're known as the variable head flow meters, in that the meters relate the pressure difference before and after the device, the flow rate. So flow is that's another thing. Lots of times we use this to try to figure out flow rates. Differential pressure manometers may be inverted so that the manometer tubing is located the pressures above the pressure sources. So this particular diagram, the differential manometer is on the bottom of that flow. You can flip it up so that it's on the top there. It just depends, like, obviously it's about ease of reading. Okay. So what do we have? Cookbook method for manometer equations. So you start at the end that you know most about. I mean, why not? If the end is exposed to atmosphere, you take this at 0 gauge pressure, 0.1, or atmospheric pressure. So in this case, you'd start at 0.1 because it's exposed to the atmosphere. And you add the terms representing changes in pressure. So that change in pressure equals change in specific weight times the height. So anytime any one of those things changes, begin at the chosen start point. So in our case, it would be 1, and include each column of fluid separately. So that one column of fluid in the mercury and the column of fluid in the water. You take the specific weights into account for the gauge fluid. Gauge fluid, remember, is the mercury. and it's denoted by a subscript G. We'll get into it again, don't worry. And the fluid to be measured is denoted as subscript F. So the gauge fluid was the mercury in this case, and the fluid to be measured for pressure is the water. And you have to ensure that you account for the temperature of the fluid, because the temperature might be different. Okay, so you move downward. If you move downward, it increases the pressure, so you add the change in pressure. If you move upward, it decreases the pressure, so you subtract that change in pressure. Okay, so that was steps 1 through 4, 5 through 8. Points within the same fluid at the same elevation may be crossed over as the pressure was the same. Remember, we learned that the pressure, independent of the vessel, as long as it's the same material, the same fluid, it's independent of the vessel. So as long as they're at the same elevation, point, in this case, 2 and 3 will be the same. And you continue, so you're like doing this step, it's a step process. So you start one point, you move away, and you continue until you get to point A, in this case, the point that you care about for the pressure, or whatever you're looking at. So you solve the equation algebraically. So it's just algebra, right? There's no calculus involved. You don't have to do any linear algebra. Oh, actually, you might have to do some linear algebra. But, you know, right now it's just one equation. You enter all the known data and you solve for whatever you're trying to solve for, okay? And in this case, it happens to be the desired pressure at point A. Don't worry, we'll do some examples. So, procedure for manometer equations, here again, more cookbook. Note, caution is to be taken when expressing the gauge pressure as a head. So a head, remember, pressure head is a measurement of length. So either it'll be in millimeters, in meters, inches, feet, smotes, whatever the case may be. So one must take the differences in the fluids into account. So that could be a difference in specific weight, difference in temperature, because the specific weight, specific gravity, all of that is dependent on temperature, and what elevation we're at. So, for example, the column in the gauge fluid at height Hg, remember subset G for the gauge stuff, is related to the height of the column of the pressure source fluid, the height of the fluid, subset F, so the pressure is equal to the specific weight of the gauge fluid times the height in the gauge fluid is equal to the specific weight of the fluid that you're interested in, so subset F, times the height of the fluid that you're interested in. So you rearrange this for the height of the fluid, so this is the pressure head, HF, and expanding for density and specific gravity, remember I said, so we've got the height in the fluid is that pressure head is equal to the ratio between the gauge and the fluid specific weight times the height within the gauge is equal to, again, the density. So density of the gauge, that ratio gauge in the fluid and the host fluid that you're interested in, times the height of the gauge. It's also equal to the specific gravity of the gauge divided by the specific gravity of the fluid times the height of the gauge. So, I mean, then you don't have to, like, say you're given the specific gravity of the something, of both the gauge and the fluid, the base, you don't have to go back and calculate what its specific weight is. You just can take it, it's a proportion, okay? So, problem 1, again, to try on your own, but we will do it, is this whole, we've been talking about this whole diagram, so let's do it. So, calculate the pressure at point A. So again, you start at a point that you know the most about, and in this case it's 1. You use that cookbook method, step by step, and then put an equation together, put all your known values in, solve for the pressure at point A. Problem 2, calculate the difference in pressure between the points A and points B of the differential pressure manometer as shown in the figure. So what do we have? All sorts of different things There's mercury in water and oil. Oh my. So they give you all the specific gravities. Again, if you don't know and it's not said, you assume that the water is at 4 degrees C at sea level. So now we're going to look at, so give those a try, okay? Handouts. So the handouts, here we go. I wonder, I've got them right here. So let's look at, which one's the first one I got here? So this one's the notes on pressure transducers. So I'll let you read this in your own time. Oh, it's kind of hard to see, isn't it? Here, let's do that. There we go. So pressure transducers, I deal a lot with pressure transducers for waves and for flow rates in rivers. So it's a device that converts the mechanical forces and applied pressure into an electrical energy. So the output signal. The output signal is linear and proportional to the applied pressure. Pressure transducers are very nearly synonymous with pressure transmitters. You'll hear them used interchangeably. The difference is a kind of electrical signals just from the outputs. So there's some minutia of transducers and transmitters. Let's see now if there's anything else that's wildly exciting here. So the pressure sensor is the actual component of the work that by converting the physical energy to electrical energy, typically fluid pressure. There, let's see now. So applications are used throughout the industry. A wide variety of applications include medical, airflow management. This might actually start becoming very important in this COVID area where we're trying to get airflow within buildings better. So that's that HVAC systems that you might have heard. These are sort of the purview of mechanical engineers. I have never had a positive HVAC experience, but that's just me. Municipal applications for what we're going to do. So you're looking at sewage force main. So you're trying to push water up a hill. Water main pressures, liquid level measurements at sewage lift stations, wells, water reservoirs, and then they say open channel fluid. So that's what I have done. Lots of yeah, you need to know the currents. One of the things that it says even here is electronic flow measurements. Oh geez, did you see in the news there's New Westminster Pier Park was on fire, and I worked on that project a long time ago, and one of the things that I did was to see if they could put in a power plant right there to get to see if the flow rates in that particular area were enough to make power, because they wanted to use it to create the lighting. It was not, unfortunately, but at the time, because it was kind of dependent on what the actual turbines could create, what they needed. So environmental, you guys might go into environmental engineering. They don't talk about that too much. Oh, maybe a little bit more. When I was in school, you didn't talk about it too much, but there's a lot of environmental engineering, environmental management jobs and work that civil engineering techs do. So this looking at river, creek, drainage, stormwater, groundwater, monitoring, all that kind of stuff. So there's some minutia in there. I'll let you guys read all that. That's the one. Now that's the other one. I think it's Bourdon pressure gauges. You probably have seen these. Here, let me zoom out a little bit so you can see it. You've probably seen these in, you know, movies where there's airplane pilots. Or say you are an airplane pilot. I don't know. I don't know what you guys did before you came into here. So it's developed by a French engineer, some smarty pants, in 1849. And yeah, you'll see these gauges a lot on like yeah, a lot of transportation equipment, I guess. So it consists of a tube having elliptical cross section. You can see it right there. Okay. So it's a tube, bloop 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 bloop. And it's bent in a circular arc. So here's our tube bent. The tube is connected to a point where the pressure is to be measured, i.e. at the socket. So here we go. There's the socket. And it's closed at the far end. When the pressure inside the tube is at atmospheric pressure, so that's that 0 gauge, remember? The tube is undeflected. When pressure is applied to the gauge and hence the tube tends to straighten and the pointer is actuated to read the corresponding pressure. So the tube changes, this little thing moves around, and you have some sort of weird calibration in there. The action of the tube is much like an unrolling of a party favor when you blow into it. So, fun. So the one shown above is a C-type. It's probably the most common one. You guys can go into that, blah, 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 blah. It's not only 2 pages. Common, wildly pressure, fluids, and gas of all kinds. Steam, water, and air up to pressures of 100,000 psi. They're inexpensive, yay. So go ahead and have a look at that. Like I said, this is a nice little, not quite as intensive video. Again, give those, as for all of them, give those a try, and if they, and I mean, like I said, it's not for marks, it's for your own brain. And then we will meet Wednesday for our live study group chat, and we'll go and do them all together. Okay?